In the previous lecture, we expressed a system of linear equations in matrix notation, as here in red. We can derive immediately a corollary of simply the notation itself. The corollary is as follows. So if the matrix A is invertible, then the system of linear equations AX equals to B has a unique solution C equals to A minus 1 times B. So how do we derive this remark? Well, so this is the quality A times X equals to B. So assuming that A is invertible, in particular case we are assuming that the system has the same number of equations as the number of unknowns. So A is a square matrix. There is no concept of invertibility of a matrix for non-square matrices. So A is a square matrix and invertible. Then we can multiply both sides of this equation by A minus 1, the inverse of A. By definition of inverse of matrix inverse, A minus 1 times A is going to be the identity matrix. And the identity matrix times X is going to be X by definition of identity matrix, which is multiplicative identity matrix. So identity matrix times X equals to X. And here on the right hand side of the equation we will have A minus 1 times B. Therefore necessarily the set of solutions of these equality is going to be the same as X equals to A minus 1 times B. Therefore there will be a unique solution given by this expression. Another important remark is the following. Let's assume the particular case in which B is the null vector, null column vector. Therefore we are in the situation of A times X equals the zero vector. So in this particular case, the system has always a solution. This is called a homogeneous linear system. It always has a solution, namely the null solution X equals to 0, because of course if you substitute for X the null vector, then A times X is going to be the null vector, and therefore this equality is satisfied. So always has a solution, and at least one solution, which is the null vector. Moreover, the set of solutions, say its set of solutions, is a subvector space of Rk. Okay, here we are assuming K is number of unknowns of this linear system, which is the length of the vector X. So how does one prove that? Well, supposed to have two solutions. Let C1 and C2, two solutions, Then, well, we can prove two things. C1 plus C2 is a solution. And lambda times C1 is a solution. So these two facts imply that the set of solutions is closed under the two operations of vector space, so sum of vectors and multiplication of vectors by scalars. So that implies that the set of solutions is a sub-vector space of Rk. So why is this true? Well, this is simply, we have to plug in for x C1 plus C2 and see if that equality is satisfied. So A times, instead of x, we have C1 plus C2. But by the distributive property of multiplication on the left with respect of the sum, so this is a property that the product of matrices has, we have a C1 plus a times C2, but each of them is a solution of this equation. Therefore it will be 0 plus 0, which is going to be 0 vector. So here we have to show that a times lambda C1 is going to be 0. Now the product of matrices times scalars commutes. Okay, so it is easy to show that this equals lambda times a times C1. Okay, so the product of matrices has also, besides being distributive with the sum of matrices, also commutes with the scalars. Okay, so a times lambda equals lambda times a times C1, but by the associative property, this is simply lambda times a times C1, which now at this point we use the fact that C1 is a solution of the system of linear equations. Therefore a times C1 is 0, so we'll have 0. Okay, lambda times 0 vector is going to be 0. So we are now here at the most important result. Well, this result is named after different people for different countries. Therefore I'm not going to attribute this result to any of them, since there will not be a typical student or listener to these lectures. I will just name this result Theorem RC. This theorem comprises two parts. The first part states necessary and sufficient conditions for a system of linear equations to have a solution, and the criteria is based on matrices. So it reduces the question whether a system of linear equations has solutions to a question on matrices. The second part, it will give some description, let's say geometrical description, of the set of solutions in the case a system of linear equations has at least one, let's say. So let's state the theorem. The system AX equals to B has solutions, which means not necessarily more than one, maybe one or infinitely many. We have seen in previous lectures, we have seen that there is no other possibility for existence of solutions. It's either finite, which means just one solution, or infinitely many. If and only if rank of A equals to rank of the matrix A, B. Okay, now you are not able to understand what the rank of a matrix A. I've not defined it yet. So what the rank of a matrix is? The matrix A is just this matrix here, and the matrix AB I will define later along with the rank. Let me state the second part also. Under these assumptions, which means assumption of existence of a solution, the set of solutions of the system is of the kind C plus W, where C is one solution, any of the solutions if there is more than one, and W is the set, which indeed, as we have just shown, is a subvector space, not only a set. Indeed is a subvector space of solutions of the following system: A times X equals to 0. This is called the homogeneous system of linear equations associated to AX equals to B. So we are still lacking of the definitions of the rank of a matrix and the matrix A slash B. Okay, so definitions. Rank of a matrix, rank of A, is the maximum, and this is very important, maximum number of linearly independent column vectors of A. Now, if we had not stated maximum, the maximum word, which is typical in any oral examination with my students, they just say rank of A is the number of linearly independent column vectors of A. But the number of linearly independent column vectors of A is most of the times not defined. It depends how many I choose between the column vectors, and according to how many column vectors I choose, there can be a different number of linearly independent column vectors. Therefore, that is not a well-defined number. But if I take the maximum number of linearly independent column vectors of A, this is a very well-defined positive integer, and it is the rank of the matrix A. Also, we can write rank of A equal to the dimension of the vector space generated by the column vectors of A. So if I take the set of column vectors of A and I take the vector space generated by it, this is going to be a subvector space of Rk if A has k rows. So the dimension of this subvector space of Rk is precisely the maximum number of linearly independent column vectors of A, and therefore it is also another definition of rank of a matrix. Now, this is more like a notation rather than a definition. A slash B is the matrix obtained as, these are called block matrices because there is one block comprising all the column vectors of A. So once I've written all the column vectors of A, then I add not algebraically, meaning I juxtapose another column vector on the right hand side of those included in A, and this vector is going to be the column vector B. So if A has H column vectors, then this matrix will have H plus 1 column vectors. Let's call the first part of the theorem part A, and the second part of the theorem part B. Now, saying that these the rank of these two matrices is the same, and given the definition of rank of a matrix and the notation of the matrix A slash B, these can be summed up. So part A and the definitions can be summed up by the following statement. So therefore, Theorem RC part A states AX equals to B has solutions if and only if B is a linear combination of the column vectors of A. Another remark is the following. Moreover, the second remark comes from the part B. Part B implies, well, a very strong geometrical property of the set of solutions of any system of linear equations. So notice that we are not laying down any assumption on A. A can be any matrix whatsoever. And part B states that if the system has solutions, this set of solutions is of this form: C plus W, where C is some vector. Well, in particular case, this is a vector, one solution is one solution of the system of linear equations, and W is a subvector space. Okay, so as a set, we are taking subvector space W, and we are summing up all the vectors of this vector space by a fixed vector C. Geometrically, this operation is called translation. Well, the set of solutions of any system of linear equations is a translated of a subvector space. So part B implies that the set of solutions of a system of linear equations is a translated of a subvector space. So subvector spaces are always linear subspaces. One-dimensional subvector spaces are just lines through the origin. Two-dimensional subvector spaces geometrically are planes through the origin, and so on. Three-dimensional vector spaces are three-dimensional hyperplanes passing through the origin, and so on. Therefore, the set of solutions of a system of linear equations will be some hyperplane, translated hyperplane somewhere in some Euclidean space.